What in the universe? Even black holes fear. Black holes are among the most mysterious celestial bodies in the universe. They can swallow light and warp spacetime. Widely recognized as the ultimate monsters, if a black hole secretly approaches our solar system, even from as far as 1 light-year away, its gravity would throw the solar system into chaos. The orbits of planets and comets would be completely reversed as it crosses the Oort cloud. The violent storms on Jupiter and Saturn would be violently stripped away. Humanity would be utterly powerless, forced to watch helplessly as Earth is torn to pieces. Continental plates would shatter like eggshells, supervolcanoes would erupt, and Earth's civilization, skyscrapers, and all living beings would be swallowed by this gravitational disaster. In the end, only a core would remain, and a gravitational duel between the black hole and the sun would ensue. The outcome of this battle depends on the black hole's original mass. Perhaps the sun might survive in another form, but more likely, like other planets, it would be torn apart, layer by layer, by the black hole, spiraling into a superheated vortex of dust and gas, completely consumed by darkness without a trace left behind. Terrifying, isn't it? Yet in the vast universe spanning 13.8 billion light-years, black holes may not be the end of the line. Above them lurk even more mind-bending monsters that black holes themselves dare not provoke. The first kind, quasars. As the name suggests, quasars are star-like objects. But they are not stars. They are active galactic nuclei of very small size but brightness powerful enough to outshine entire galaxies. Their luminous regions may span only a few light days to a few light years. Yet within this tiny space, the emitted light equals that of hundreds of billions of suns. Their brightness is hundreds of times that of an ordinary galaxy. The energy they release every second dwarfs even massive galaxies. To date, humans have discovered over 200,000 quasars. Only about 40 quasars are more than 127 billion light-years away. Among them, the largest quasar is a hyperluminous quasar 128 billion light-years from us. Its luminosity is 43 million billion times that of the Sun, born just 900 million years after the Big Bang. Like the brightest lighthouse in the distant night sky, shining dazzlingly. Consider yourself lucky Earth does not have such a neighbor. In fact, quasars are more like supermassive black hole systems on fire. At their center lies a supermassive black hole greedily devouring matter. For example, the central black hole of that hyperluminous quasar has a mass 12 billion times that of the Sun. During the black hole's feeding, an ultra-hot accretion disk forms, and relativistic jets near the speed of light shoot out along the poles, like blazing spears piercing through the darkness of the universe, capable of penetrating an entire galaxy. The second kind, voids. Voids are not celestial bodies, but regions of extremely low matter density within the large-scale structure of the universe. On scales of hundreds of millions of light-years, galaxies connect like vines into massive fibrous networks. And voids are these enormous, almost empty 3D cavities between those networks. They are not entities made of matter, but vast areas with extremely low matter density and sparse galaxies, known as the universe's starless zones. To black holes, voids are desolate wastelands. If a black hole falls into the center of a void, it will find no gas or stars to feed on. Its accretion disk will go dark from starvation. Jets will cease, and it will eventually become a hidden, unobservable, silent object in darkness. Here, even black holes that devour everything have nothing to consume. For matter, voids are gravitational vacuums. The matter inside is so sparse that gravity is extremely weak, making it difficult to sustain even a single galaxy. The largest void discovered by humans so far is the Boats void, located in the direction of Boats, with a diameter of 330 million light-years. Its interior is almost empty, with only a few isolated galaxies. This discovery changed humanity's understanding of the cosmic structure. The universe is not uniformly filled with galaxies, but resembles a huge sponge or foam, with the cosmic web of galaxies enveloping vast voids. Voids occupy most of the volume of the observable universe. Most astonishingly, we might be living inside a void. Research in 2013 suggested that our Milky Way, the local group, and the massive Laniakea supercluster may all lie within a local low-density region called the KBC void. This void could be as large as 2 billion light-years in diameter. If this is true, then the average universe we see when looking at the stars is actually the view from inside a giant void looking outward. This may partly explain the Fermi paradox. The reason we can't find extraterrestrial civilizations might not be their rarity, but because we live in a suburb or desert of the universe, where matter and galaxies are unusually sparse, like living on an isolated island in a vast ocean. The third kind, Gravistar, gravitational vacuum star. You can think of it as a black hole substitute, but it is fundamentally different from a black hole. Black holes are perfect products of general relativity. They have event horizons, eternal walls of despair, from which nothing, including light and information, can ever escape or be seen again by our universe. But gravistars have no event horizons. They obey quantum mechanics. which suggests that at the final moment before an event horizon forms, an incredible internal repulsive force originating from quantum vacuum prevents complete collapse. This results in an extremely dense object with gravity close to that of a black hole, but without a delete button. Matter and information may be infinitely stretched and trapped, but theoretically never disappear forever. Simply put, it is a quasi-black hole frozen in time. It arises from a century-old problem. Hawking proved that black holes evaporate, but this causes a fatal paradox. Where does the information falling into a black hole go if the information disappears forever as the black hole evaporates? This violates the fundamental quantum mechanical law that information must be conserved. Therefore, some physicists in the early 21st century proposed that stars may never collapse into black holes. At the critical point of event horizon formation, quantum effects trigger a vacuum phase transition, like water suddenly freezing and releasing energy, producing a repulsive force that stops the collapse, forming a gravastar. In this way, information is preserved on its surface or inside. Its very existence means black holes might not be the inevitable endpoint of massive star death. However, gravitational wave detectors like LIGO and Virgo have repeatedly observed black hole merger events, and these gravitational wave signals match perfectly the predictions of general relativity for merging black holes with event horizons. This makes the existence of gravastars increasingly unlikely. Still, many mysteries about black holes remain, and the answers to these questions may only come with more advanced technology in the future.